7.4 Properties of Logarithms. At the end of the semester, sections 1, 2, and 3 from chapter 7 was a quick review of exponential functions, and then an introduction to what is a logarithm. And that was it. Just what is it, and how do you look at it? So that meant you guys would be able to see something like log base 4 of 16. Understanding, first of all, how to write this. The log and the 16 are all written on the same line, and the 4 is a subscript. So you have to understand how to write it. Some of you guys are writing things like this, where it's log base 4 and then a 16 sitting up here. That doesn't mean anything. That's nonsense. Lack of sense. So we have log base 4 of 16. So we discussed that log base 4 of 16 equals 2. Just what is a logarithm? What does it ask for? 4 raised to what power gives me 16? 2. That's what a logarithm is. Section 4 is going to discuss. We are discussing how a logarithm behaves. We have 3 main properties up here. All 3 of these are very important. The third one is probably the most important, and I'll explain why in a minute. But we have the product property, which tells us that log base b of m times n is log base b of m plus log base b of n. They're all variables because it doesn't matter what the number is. It works out no matter what the numbers are. And make sure you understand that the base here, base b, is the same as the base here, base b, as well as here. It's going to be the same base all the way across. But if you're multiplying things together here, you're going to be adding things together there. Because the properties of logarithms are very closely related to the properties of exponents. And you can remember that when you multiply things with exponents, like x squared times x cubed, you would add those powers together, and the result would be x to the 5th. And we're actually going to prove the product property, and it's going to use that property of exponents that I just referenced. So you can see the quotient property is very similar. It's just instead of multiplication here, it's division. So the only difference is instead of addition here, it's subtraction. Now the power one, all 3 of these are important. You're going to use all 3 of these a lot. So I'm going to tell you that the power property is the most important one. Do not mistake that to mean that's the only one that matters. That's the only one you're ever going to use. You're going to use all 3. But the power property one I call the most important because those problems from the review sheet for section 3, where it was an equation with exponents in it, and you had to rewrite everything with a common base in order to solve it, and none of you liked it, and it was difficult and complicated. This power property, we will see, not today, but later, we will see that that allows us to solve those types of problems much easier. That's why logarithms are very important. So now, to prove the product property, this is the one we're going to prove. I want to say that m is b to the x power, and that n is b to the y power. I'm just going to say that because I know what's going to happen in a minute. So why did I say that? Because I know things. That means that we can say, rewriting those as logarithms, log base b of m is x. Similarly, log base b of n is y. My setup is complete. Now I just want to prove it. I know from right here that m times n is b to the x times b to the y. From that first line I wrote down. M is b to the x, n is b to the y, so m times n is b to the x times b to the y. We know, using the property of exponents, that that equals b to the x plus y. So that's the step where we're illustrating the fact that the properties of logarithms and the properties of exponents are very closely tied together. So now I'm going to take this little guy, I'm going to ignore this middle step, not because it's unimportant, but just because it's going to make what I'm about to do more clear. I have m times n equals b to the x plus y. That is an exponential statement that I can rewrite as a logarithmic statement. I can write that as log base b of m times n equals x plus y. Then we can look at this line right here. We know that x plus y is log base b of m. We know, x plus y is log base b of m plus log base b of n. And that's it. Because there we have log base b of m times n is log base b of n plus log base b of n. So when you are given multiple logarithms and asked to rewrite as a single logarithm, another word you may see there is condense. Asking you to take an expression that has multiple logarithms and condense it into one single logarithm. And you always want to simplify whenever possible. So in part A, the first thing I can do is say log base 3 of x minus log base 3 of 49. That is the power property. Right? This 2 here can be moved inside as an exponent, giving me log base 3 of 7 squared. And 7 squared. From there, I can write this as log base 3 of x over 49. That is the quotient property. At that point, I cannot condense anything more, so I'm finished. That's it. It's just like when we were factoring polynomials. How do you know when you're finished factoring? When you can't factor anymore. Which is a little bit more difficult because you have to know whether or not you can continue to condense Mr. Part B. Part B, what I'm going to do? Use that first property, log base 8 of 48 times 4/3. So that is the product property. We have condensed it as far as we can. That's true. Second part of the instructions, though, if possible, simplify. In part A, we couldn't simplify. We have no idea what x is, so we can't do anything. Part B, however, part B we can simplify. We know that 48 times 4/3 is 64. And we know that log base 8 of 64, it is 2, thank you. So this type of problem, opposite of what we were just doing. You're given one logarithm, you're asked to expand. So part A. First thing, log base 5 of 125 minus log base 5 of x times y. That's the quotient property. You have log base 5 of a quotient. You can separate that out using subtraction. And again, we want to keep in mind that we want to simplify however and whenever possible. So log base 5 of 125, some of us may know that off the top of our heads, but this is log base 5 of 5 cubed. And then over here in parentheses, I'm going to have log base 5 of x plus log base 5 of y, using the product property. If for this portion it's not clear that the answer should be 3, what we can do is use the power property and move that 3 out front. We have 3 log base 5 of 5 Log base 5 of 5, that should be clear to everybody. 5 raised to what power is 5? 1. So we get 3. So what we have here is 3 minus log base 5 of x minus log base 5 of y. Part B is a bit more straightforward. We're going to use the product property. That separates out as log x squared plus log y squared plus log z to the negative first. What is the base of the logarithm in this problem? And we just have to remember that if there's no base written, what's the base here? Nothing's written there, it's a 10. If there's no base written, it is 100% of the time a 10. The only exception there is if you take graduate level mathematics. We go through and use the power property to get 2 log x plus 2 log y minus log z. And that is our complete expansion. Change of base formula. Some people in here have a calculator whose operating system will allow you to do logarithms with bases other than 10 or e. And it's very easy because the way it shows up and asks for the information, it's very obvious where things are supposed to go. That's the new operating system on the calculator. If you have that, feel free to use it. I don't care. If you have the older operating system, there is not a nice convenient way of doing logarithms with bases other than 10 or e. The easiest way to do it is using the change of base formula. So an example that we shouldn't need the calculator for, log base 8 of 64. We know that that is 2. But to put that in your calculator, you would say log of 64 over log of 8. Where since there's no base written, this is base 10. And how do you remember which one goes in the numerator, which one goes in the denominator? The number that is physically written higher on the page is the one that should be in the numerator. The one that is physically written lower on the page is the one that goes in the denominator. And if you put in your calculator log 64 divided by log 8, you should get 2 exactly. Part A, what is it? 2.1. Give me 4 decimal places. 2.1434. And then part B, if memory serves, is exactly 2/3. So again, all we had to do is read the problem. This word problem actually defines the variables for us, gives us the formula. We just have to realize that they've given us the distances, and therefore we plug in for D. And when we plug those two things in, we should get, for speed 1, we should get 176.9832 miles per hour. And for my second speed, we should have 148.9874 miles per hour. So you revisit the word problem, you say, oh, all they want is the difference. So you find out what is S1 minus S2. You plug that in and you get that it is 27.9958 miles per hour. Okay? So the tornado that traveled 16 miles was going 27.9958 miles per hour faster than the tornado that traveled 8 miles.